I'm Jim Colander, and I'm here representing 2I2C at the Jack Eddy Cross-Disciplinary Symposium. And together with my colleague Fernando Perez and others, we deployed a Jupyter Hub to support collaboration at the symposium. And a lot of the participants here are partially familiar or not so partially familiar with the ways to use these resources. And so Fernando and I have been providing technical support to try to get people up to speed on how to use these tools. So last night, right before I went to bed, I saw that there was a technical support question from Greg Cook, and Greg was asking, how do I get access to this data set that's hosted on Caltech, the NASA Exoplanet Archive? And I knew a little bit about how to do that, so I told him, and then I made a little notebook that showed him, and then he used that notebook to supplement things that he was working on previously that I knew nothing about. He just asked about whether or not he could get access to this data, and the way he was going to use it was not clear to me until I talked to him later this afternoon. Now, the kinds of things that he was trying to do, I think, were first articulated as a really important scientific question by his PhD advisor, Dan.
I'm Dan Marsh. I'm from the National Center for Atmospheric Research, and also I'm a professor at the University of Leeds. The scientific problem we were interested in is whether or not exoplanets have atmospheres, whether they can hold on to their atmospheres, especially when they're orbiting close into a star that has really strong UV output. And so the question I said was, why don't we take our global model and try hitting it with these various solar spectra from these different stars? And so then Greg started looking into the various data sets, and we realized and at this meeting we started talking to people and realized that there's big uncertainty in these. And so Greg thought, we said, well, why don't we figure out a way that we could actually test all that uncertainty by pulling in various spectra from the stars and making them so that we can use them in our model. And so Greg is working on the tools based on Jupyter Lab or Jupyter Hub to create these spectra for the models.
So I'm Greg Cook. I'm from the University of Leeds in the UK. I'm a third-year PhD student now. So the idea was to create a really open source tool that everyone in the community could use. And it's nice because if you create an open source tool and everyone understands it and it's easy to use, then everyone in the community is using the same method to create these stellar spectra scaled to various different planets. So the idea was to create something that you can open up a notebook on Jupyter, and you don't have to go to any other websites to download any of the data. So we just pull in the data using various commands from all these different websites, such as the NASA Exoplanet Archive and the Mussels database, which has all of the stellar spectra that have been observed recently for exoplanets. And to make it user-friendly, I've been using drop-down menus in Jupyter, little widgets where you can just make certain option selections rather than having to type anything in the code or change things in the code from true to false or anything like that. It's just drop-down menus the whole time. So the idea is you say pick a star. A famous one in the exoplanet community is TRAPPIST-1. It has 7 terrestrial rocky exoplanets that are all roughly Earth-sized, which is exciting for many, many reasons. And you say, okay, I picked TRAPPIST-1. It pulls in the spectra from the Mussels website of TRAPPIST-1. But that spectra is scaled to the irradiance received by the Hubble Space Telescope, which is really, really low, and we want the irradiance actually 30 light years away at the planets. So then you say, get a drop-down menu from the NASA Exoplanet Archive of the 7 planets, TRAPPIST-1b all the way to TRAPPIST-1h. And these have a certain distance from the star. They have certain orbital periods and different sizes, different gravities. And you can get all that information from the NASA Exoplanet Archive. So that's what Jim helped me pull in using a command that I didn't know how to use. And you get all that information, which then helps me rescale the spectra to get the correct irradiance at each planet. So if I wanted to get the irradiance at TRAPPIST-1b, that's several times the irradiance that the Earth receives, so it's really hot. Whereas if I go to TRAPPIST-1h, which is the furthest away, then the irradiance is a lot lower than what Earth receives, and that planet is really cold. And once you've selected your planet, it then rescales the spectra based on the information from the NASA Exoplanet Archive, and you can put that into any atmospheric model, such as Wacom that me and Dan have been using, or say Rocky 3D, which is a 3D model used at NASA, or various other 1D and 3D models that the community uses. And the idea is, basically, it should take about 5 minutes maybe to go through this and get a spectra that you can then plug into a model. Whereas originally when I did it for the simulations that I started a year ago, it took me about 5 hours to do one planet. And now you can do, say, with this, once it's finished at least, you can do maybe 10 spectra in 5 or 10 minutes. So hopefully it'll be really useful for the community. We'll put it on GitHub and tweet it and try and get everyone using it. And maybe it'll be adapted not just for exoplanet atmosphere models, but it could also be adapted for escape models and I don't know, there's probably more applications as well that I can't think of.
Hi, my name is Fernando Perez. I am a professor at UC Berkeley in the Department of Statistics, and I am a co-founder of both Project Jupiter, which is a collaboratively developed set of open source tools for interactive scientific exploration of data and for discovery and for scientists. I was invited to participate in this heliophysics community event in asking ourselves the question of how could our tools that we use in these other domains help this community, because ultimately the purpose of this infrastructure that we've created around Jupiter and related projects is really to assist scientists in not only analyzing their data, but in working together, in discovering new ways of accessing, of understanding, and of sharing with others those tools. And so this has been an opportunity to connect with this community. We've been teaching them some of the things that we know, but especially trying to understand what are their questions and how can these tools support and empower this community, and to connect with other scientific communities where maybe there are new problems at the intersections of two spaces. We have a colleague from CU Boulder and Colorado School of Mines who works in cryosphere problems coming tomorrow to this event to think about how could similar problems across communities that ultimately connect around our planet and its climate work together in answering new questions. And I'm delighted to see what Dan and Greg have done in just the span of a couple of days, and really moving forward and accelerating their ability to discover the kinds of problems that their domain is asking, with these tools that are open to everyone, from an undergraduate first semester student at university to cutting edge researchers like themselves.
The International Interactive Computing Collaboration, or 2I2C, combines expertise from Columbia, Berkeley, the University of British Columbia, and a lot of experience in delivering these interactive computing tools and data analysis methods. And when we learned about the Jack Eddy Symposium, which was pretty short before its start, we had the idea and asked the organizers if they would be interested in having a Jupiter hub that was kind of tuned or curated for use in the heliophysics community. And thanks to the fabulous engineers on our team, we managed to stand up a hub. And then during the course of the symposium, we've spent some time training people and helping people learn how to use it. And it's that way that technology facilitates collaboration that I think is really special right now. And then this event with the movement from a successful analysis, but with some significant effort of one star being accelerated into an intercomparison across many stars that Greg saw how to do once he had access to the tools. I think it's just an example of the kind of acceleration that technology and collaboration can facilitate really across the whole domain of scholarship. I mean, it's not just a scientific tool, it's also used in social sciences and digital humanities. But what we were trying to do is to take this very robust infrastructure and customize it for the heliophysics community. We've got some rough edges, but the success of this collaboration, I think, is a signal that a little bit more work on this and a little bit more effort on this has outstanding potential.
Yeah, I'd like to add that this technology that's been stood up for this meeting and these sort of tools are transformative in terms of education and allowing PhD students and master's students to quickly get their science done without having a lot of overhead and learning. And we're putting the tools right in their hands very quickly. And it's exciting to see how they can just, in a few days, start looking at data and interrogating the data. And so it's amazing. It's a real step change from what's happened before.
For me, this project and this journey has been a combination of two motivations that sometimes are put as if in competition, but that I think this event illustrates that they're very much in harmony, which is the dual desire to accelerate scientific discovery and at the same time to improve access to science and to the tools and to open up the process of not just learning but participating in scientific discovery to many more. Many of the ideas that we're seeing today in action are motivated by my own experience when I was an undergraduate in Columbia studying physics and not having access to the computational technology that was proprietary and expensive. And over 2 decades, the efforts of many have made it possible to have these tools that, on the one hand, allow me at UC Berkeley to teach data science courses where I have 1,200 students starting in the fall in a way that would be unthinkable if it weren't for these tools. And those students are going to go on to take jobs in industry, jobs in government, to do scientific research and discovery, even though they're undergrads. And yet at the same time, we can see how putting them in the hands of a new community who has their own questions, when we marry kind of the infrastructure with the local context of their data, their knowledge, their needs, does also enable discovery, right, at the edge of science. And so that this notion that allowing tools that with the access with an internet web browser and a computer can allow anyone in the world with an internet connection to see and learn about nature and at the same time do cutting edge discovery, that these two things are actually not in tension. They're quite the opposite. They're in complete harmony, and we can achieve both goals is very motivating. And it does take the combination of academics, industry, nonprofit organizations like the teams we're creating at 2A2C to make this possible. And the challenges we have today in science are very much at these boundaries that the Jack Eddy Symposium is all about. It is about interdisciplinary collaboration. It is about connecting data sets that we may already have them, but we couldn't quite put them together. And Greg and Dan's work is an example of how that access to connecting the data sets, which appears quantitative, it is just going from 5 hours to 5 minutes, but that is qualitative. There's a point where that quantitative change opens new qualitative boundaries. They can ask new questions and they will make new discoveries, and that's exciting.
I'm Lika Guhatakurta, heliophysicist at NASA headquarters. Have been involved with Living with the Star program for actually one magnetic solar cycle, which is 22 years. And what we are doing here, we are actually honoring the life of Jack Eddy, one of the great interdisciplinary scientists of the previous century. He's the one who actually connected sun to climate, sun's variability to climate by studying growth in tree rings. So we create this symposium about every few years, really to bring scientists, engineers, data analysts from various disciplines, so that we are not siloed into our science, and really work at the intersection of the science boundaries to kind of figure out new science, new discoveries. And what's been fascinating in this workshop is there are so many people from so many disciplines. My brain is actually completely stormed. And then this afternoon, I just hear, just by walking in the hall, hey, guess what happened? We have a graduate student, who was looking at one exoplanet, and then he started using the Jupyter notebook and got access to all the archival data of exoplanet from Caltech. And now he can do comparative study of exoplanet. And when you hear something like that, that absolutely strikes you and blows you away. This rapid pace of accelerating science discovery through things we already have, but infrastructure and data that we didn't connect before. And that's what has just happened. To me, it is like no short of a miracle. So with NASA's lead on Open Science Initiative, which has been sort of a cross-cutting theme across all of the science talks in this meeting, and really seeing the accessibility and usability, with the right kind of interface for this particular software package, which is kind of being offered to this workshop as a donation from the nonprofit 2I2C. I think these, when I think about it, it just seems like, we are actually sort of transforming the way we do science for the first time in 21st century. Like, we are bringing data, we have already trained the students with science, and they can now take models, data, you can make all of these available through your Jupyter Hub. And you can arrive at scientific queries that would have taken you years back in the days when I did PhD.